My name is Travis Phillips. I'm a senior security consultant with Secure Ideas, and today we're going to be discussing on the topic of firmware hacking. This is something that I kind of did as a career for about 5 years straight, just doing nothing but embedded systems security. So I actually kind of developed some skill sets in firmware hacking and found that it's actually a skill set that not a lot of people have. So I figured it would actually be a good topic. So overall, this is going to stay a fairly high topic level conversation. So, but before we begin, I wanted to kind of throw out a disclaimer here about some of the legality of this. So do keep in mind that reverse engineering efforts generally tend to breach IP laws, intellectual property laws. So generally, it's best to get permission first before you start to do that sort of stuff. So if you're dealing with something that's kind of in the public, you might be able to find some items that might have a bug bounty. If you're doing this sort of thing professionally, then just make sure that you've got an SOW and an NDA in place, and that it explicitly calls out that you will be doing reverse engineering efforts, and that will help you get around it. Now, if you don't really have a target that has a bug bounty or not doing this professional, you're just trying to do this as a hobby, then you've got options as well where you can try to just roll your own firmware. Using something like OpenWRT was what I did for the demo that we'll be working on later today. Since the source code is fully available for that and the toolchain to build a firmware, you can do that. And that would give you, you have the source code for it. And two, this is a binary that you produced. It should be perfectly fine for you to reverse engineer that. And then the final point there is I am not a lawyer. So if you need actual legal advice, talk to an actual lawyer. I've never even played one on TV. So, yeah. So what is firmware? So the firmware is, there's a lot of definitions on it, but my definition has always been it's a little binary blob that will be installed on some sort of device, some sort of hardware device that's actually going to drive the logic of the device. Now, I kind of break this into two flavors. There's low level and high level. And today's talk, we're going to mostly focus on high level. So low level would be firmware that is designed specifically to target a particular type of MCU, microcontroller unit. It does not have a very robust operating system. It might be like an RTOS, or it's going to just be direct code that runs something. Think like Arduino, for example, or a PIC microcontroller. This can be, I'm not sure about that one, but it might be into that camp. This is about the Simon Centrifuge controller. I'm not sure if that's a high level or a low level. Probably low level. But yeah, so that's that sort of thing. On the high level, we would actually have things that would be an actual full-blown operating system on them, and it's usually going to be some sort of Linux embedded system. For example, we had discussed OpenWRT. It's a great example of that, but generally they'll do this sort of thing if they need networking functionality. Like they operate, like you want a complete operating system because I need a full network stack. I'm making a network device. I'm making a wireless access point. I'm making a switch or a router or firewall or camera or whatever. This device needs this, and I don't feel like reinventing the wheel, and I'm not going to. So I'm just going to use Linux, which you can do. It's free and open sourced, and just put it into the thing and do that. This also usually makes so it's a little easier to transition to some hardware. There's going to be some independent circuits and stuff like that they'll have to maybe change some stuff for, but usually it's not that bad. So a lot of developers will actually go with a high level OS or a high level firmware. Usually the constraints being the size of the flash. So like low level would be, like I said, car radio or remote controls for a TV or something like that. Would be a simple circuit, and we're not going to take the time to put a big NAND chip on that. So we would probably go with something more direct, low level versus high level. Yeah, just install a NAND. So why would we want to focus on hacking firmware? So firmware, for the most part, has gone unseen and usually never gets underneath the microscope. A lot of times, especially up until more recently, there weren't many tools for this sort of thing. There weren't many people that had the skills for this sort of thing. And a lot of times these things could have vulnerabilities and literally make it from sunset to, end of life and decommissioned before anyone even found out there was a bug. Another reason that I always kind of found it interesting with firmware was the fact that if you found a vulnerability in a version of the firmware, it worked on the entire ecosystem that was running that version. So if you had one exploit, it would work on that entire ecosystem for that version. And a lot of times these things had some sort of canary that would make it possible to dork it with Shodan or Google Dorks or anything like that. So, and once a patch comes out, a lot of times if these systems were not doing automatic updates, which a lot of times they don't, a lot of these embedded devices are set it and forget it devices, they never got patched. So they might have vulnerabilities on them that are 3, 4, 5 years old and still be out there. So another thing about IoT devices is that they're generally headless, which means that the device owner really, unless they're monitoring network traffic, they generally don't know what it's doing. There is no way to check what processes are running on it. There's no way to install endpoint protection, antivirus, or host-based IPS or anything like that. They're blind to what's going on the device, which meant that as a threat actor, having a shell on that's not a bad place to be. You'd have a root shell on a Linux system on your network. It's not a bad place to be, especially when you can't monitor what's going on with it or even access that system to figure out what's doing it. All you could do is isolate it if you saw something weird happening. So we are actually seeing in the wild as well that threat actors are starting to target embedded systems. We've had push to kind of make it so it's easier to handle MIPS and ARM binaries and stuff like that. And I think in general for the industry as a whole, or anybody that's even using technology, it's really time to start taking the security of these devices a lot more seriously. So when we're talking about the firmware, we want to analyze it. We have to first obtain it. So we have to discuss some of the methods for obtaining it. Now, I am a fan of the ideal of always try the simplest method first. And if you're doing this professionally, just ask the vendor. Most of the time can get you a copy of the firmware. A lot of times you're going to want to make sure that you've got a copy of the firmware that is decrypted, in case you have some vendors that will actually ship encrypted firmware, and then the device's update process is supposed to decrypt it. Make sure you ask that it's a decrypted firmware and do that. And as long as you got an NDA in place, a lot of times vendors are okay with that. Some vendors as well, if you're not doing this professionally, but say you're looking at bug bounties or just whatever, some vendors actually have the firmware available for download on their website. So two vendors that kind of come to mind was Netgear and TrendNet. They make various networking equipment and other little like household embedded devices. You can look up your model there, go to the support page, and you can find the firmware for your model, so that way you can flash the update yourself. And if you want it to, you could actually have a copy of the firmware that way. There are a lot of vendors that will actually do that, and I've had some tests before where I've needed to test something for a system, and when I asked them for it, they're like, just go to the website and get it. So it's worth doing that. Another option as well is sometimes some of these devices have automatic updates, and they will actually just request the firmware from their servers over a clear text protocol such as HTTP. And at that point, just capture the network traffic with Wireshark, and you can extract it. And at that point, you'd have the bin file. So these are the basic methods. Now we'll go on to more intermediate methods. So if you have a method for getting a shell on the system, this can be by it's running Telnet or SSH and it'll let you in, or you found an exploit that can get you a shell on the device that was already publicly available, or you took the device, opened it, and you were able to get a UART, to find a UART interface that would actually allow you to get a shell on it that way. You can find most of the time that NAND flash would actually be under /dev/mtd, and then it would be some sort of number. Those would be the various partitions that are on the flash, and you can actually use DD to dump those out. And you can actually, most of the time, you'll find a lot of embedded systems that are Linux will have at least one tool or another that will let you export it out, because a lot of times size constraints become a problem on embedded systems. This would actually let you dump the firmware. And this also has an added bonus that usually one of these MTD blocks that are on there is used to store user configuration settings. So you actually get a copy of that, and you can see how that's laid out, which can be useful for some of your reverse engineering efforts. Next up would be the more advanced methods. I'm growing a little bit more fond of this method lately. It's just been kind of fun to do, but physically dumping the firmware from the flash chip is kind of neat, but it does require some investments. It requires like a hot air station makes removing those NAND chips a lot easier, because a lot of times they're going to be TSOP or something along those lines. Universal Programmer, you can pick these up from like Ollie. Mine's just like a little cheap one from Ollie that came with some adapters and stuff, but you will still find yourself needing more and more and more adapters because of the amount of packages that are out there that are available for some of these ICs. So you will definitely be adapting. These programmers here as well don't necessarily guarantee that it's going to cover a chip that you come across either and let you dump it. But most of the time, I've had pretty good luck with that working. Again, as a bonus, you do get the full dump of the chip. So if there were settings and stuff stored on that, you got those as well. And you will be amazed at how often those are going to be in clear text. So if you had a device that you set up a password, you more than likely can dump that flash and you'll probably find your password clear text. Same thing with if it connects to your Wi-Fi network, the WPA2 key would be there, which is terrifying with the amount of stuff that we're actually putting outside, like smart home stuff that we're putting outside of the house nowadays. That's kind of a interesting risk to consider if it's outside. So there are some drawbacks to this as well, which is it is also very easy to brick a device this way if you haven't quite mastered desoldering chips. When I was first starting this out, I did this actually quite a bit. And at that point, you break the flash chip and you've lost your firmware and you've lost the device. It's just not going to work for you anymore. Another option is JTAG interfaces. I personally don't have too much experience with this, but a JTAG was a debugging interface. It was supposed to be kind of a protocol for being able to debug systems by being able to control interrupts and stuff like that and directly control CPUs. And with that said, you can actually use that to access and dump memory from from the JTAG interface. I've personally not done too much with that. I've heard people doing that stuff. I don't know too much about it. So sorry, you'll need to do your own homework on that one if you want it to go that route. So using one of those methods, you'd probably end up with some sort of binary file, some .bin file that's there. So cool, we got that. Now what? There's a few commands that you can start off by running, such as strings. Will dump out, ASCII strings that are there that might give you a little bit of a hint on what's going on. The file command can sometimes help if it's a well-known firmware. There might be signatures that in there that Magic and File might even know how to decode some of that if it's a well-known firmware. But a lot of times it's just going to report data because it doesn't really understand what it's looking at. There's no magic. If you're not familiar with what I mean by magic, most files at the beginning, the first couple of bytes will be a unique signature. Like ELF will kind of actually have ELF, or an executable file for Windows will normally have MZ at the beginning of it. These things are magic that allows a program to open up the first few bytes of a file and then just read that and go, yep, okay, that looks like what I'm expecting. So let's proceed. Or if, you read the first 4 bytes of a file and it's not what you expect, just go ahead and stop processing it. So, but there are other options as well. You've got hex editors on the free side in the Linux world. There's Bless and WX hex editor. I've been kind of swaying a little bit more on the free side for WX hex editor. It just seems to be really nice and stable. And then in the commercial space, if you wanted to do this, and I found this to be incredibly helpful when I was doing a lot of this embedded firmware hacking, because of the fact that you deal with so many proprietary formats for things, was 010 editor. What was really great about this editor was the fact that it had a templating system. And you could actually create a template, which was like almost like writing a C header file that explained how structs work. And then you would explain this file kind of uses this structure system. And at that point, it could highlight, and actually, if you like opened a file that template applied the template, it would basically almost explain the file, and you could actually have it do color coding on syntax and stuff like that for this is this data structure and so forth. It was really helpful for that. There's also a repository that will let you download other templates that other people have already written, which they already cover quite a few file formats. So, but that stuff was really good. But yeah, all these are really nice, but ultimately, we know that this thing probably is running Linux. And what I really want to get at is that file system. So what we actually need is we need a better tool than file. And that is where the tool Binwalk opens up here. So Binwalk was a tool that kind of works like magic, or the file. Like file usually looks for the first magic signature that it has and then dumps that as the file is this. Binwalk does that, but just keeps going and keeps looking for more signatures. And it's very useful for that. And there's a lot of cool features in there. Like there's a nice hex compare feature that's really cool and does color coding to show the difference between two files if you have two files that are very similar. I've actually found that to be helpful with configs. If you dump a config, change something, and then dump the config again, and you think it's encrypted, you can use that to tell if it's just changing this little spot where you changed the setting, or if it's the entire thing's changed. It can be useful for that, but ultimately it's very useful for finding everything. And then it's also useful because it has the ability to extract these things. So there's like Stego is also another place that this is really kind of a cool tool for, but we're using this in terms of firmware. And what was really good about that system was that if it found something that looked like an embedded file system, such as SquashFS, JFFS2, or a CPIO, or something along those lines, it would attempt to extract that file system and see if there's a root file system on there. And if it is, it will actually just dump that entire thing out to a folder if you provide it Binwalk was the -E switch. So, and that would go out to a folder that would be named similar to your firmware file. So in this case, like in this screenshot here, I've got firmware, the date, timestamp, .bin. We run Binwalk on it. We can actually see it do a dump, and it shows, we've got these various artifacts that it found. So it would show you in decimal and hexadecimal the offset of where it found that magic signature. And then you would actually have, like, there's this LZMA, compressed data. That's interesting. But we also have a SquashFS that occurs at 0x2A0000. That is more than likely going to be the root file system. And we are actually able to run this with the -E switch, and it would actually have extracted this. And what it does is it will extract it to a file that will be named after the firmware, but it will have a underscore at the front of it, and then .extracted at the end of the folder name. And if they found a file system, you can see underneath that folder, it will actually create this squashfs.root, and you would have that. So if I, let me do this, I've got a VM up. So there we go. So let me see screen. This is it, right? Yep, there we go. So I've got this firmware file here. And if I just run Binwalk against it without that switch, what it'll do is it will just dump out the list of that information of what it found. It doesn't extract anything yet. So we don't have that underscore file yet. But if we actually run this with the -E switch, it will dump that information out again, but this time it'll actually run the extractors. And it tried to run a few different extractors here, and I don't have these Sasquatch installed particularly, but it did have another tool that it was actually able to use that would actually allow it to extract that firmware. And under here, we have this folder, the firmware that starts with the underscore dot extracted at the end. And we actually have a squash fs-root. And if we change directories into that, we can see what actually looks like a normal Linux file system. And for all intents and purposes, it basically is. So that's how we would extract the firmware. And at this point, we've got the root file system for the firmware, and we can proceed from there. So what we'll do is I'm going to switch back to my slides now. Let's see. It's this one, right? Nope. Nope. There we go. So once you've gotten the file system extracted, now what? Now you're going to attack this thing thinking about this almost like a forensics is what you're going to want to do. You've got a copy of the system, the file system that is on the device, and it's time to start exploring. So what you're going to want to do, usually how I would normally, my workflow for this sort of thing was, I may have the firmware and I may have never even have cracked the device open yet. So my goal is going to be to determine the architecture. I want to know, is this, what is it? Is it x86? Is it MIPS? Is it ARM? PowerPC? What is this exactly? So once we can, that's pretty quick and easy to establish. I also like to spend some time looking into the etc folder. That directory usually contains a lot of configurations for things, and reviewing the boot up process. So most devices are designed to be set it and forget it. So you plug it in, power it up, and things start, and it's ready to go, and it's doing its thing. There has to be some sort of chain there that starts all that up automatically without user intervention. So usually that's going to be the init system or something like that. Another thing that I've always found really important whenever you're looking at embedded devices is look at the firmware and see if you have static public and private key pairs. So for SSH or SSL, it's not a bad idea to look for those sort of things. And then finally, you move on to the fun part, which is the hacking part, which is go explore and look for exploits. So determining the architecture, like I said, that's fairly straightforward, quick, and easy to do. Usually I just go into the bin directory. You're usually going to have BusyBox or shell, one of those two, run file on that thing, and it will tell you that this is a ELF32-bit, least significant bit executable, and it's ARM. So at that point, we are actually able to determine that this is a ARM binary. So at that point, all the other binaries should follow suit. You at least know what sort of architecture you're working with, which is going to make your reverse engineering efforts as well as your exploit development efforts easier. So underneath the etc folder, you're going to want to look at the message of the day and banner if there's one. Sometimes these will have drink recipes, or it can actually be some sort of internal devs thing. Next thing to do as well is check to see if there's a password or a shadow file. This is where user accounts and passwords are stored. If this is static in the firmware, that means that these logins should work across the entire ecosystem if you can crack them. Also, the other thing to check is root the only user on the system? Surprisingly, this is a lot of the times the case. Everything on an embedded system often runs as root. And then if you only have root or some other privileged user, how secure are these password hashes? Seriously, just try to do a mask attack with John the Ripper and just go characters 1 through 8, all characters run. You'd be surprised at how many times you will successfully crack an embedded password or an embedded systems root password that way. And I was trying to show this off, but that list on the right, if you guys recall a while back ago, there was the mirror botnet that ended up launching a distributed denial of service attack that had over a terabit of traffic in the flood. Very powerful system. It was completely built off of embedded systems such as DVRs and smart lights and hubs and stuff like that were on the internet. And its method for spreading was hacking Telenet that was on these systems using this password list that it found was attached to a lot of these embedded devices. But the thing is if you find that one of these passwords works for this particular type of device, and there's 100,000 of these things on the internet, congratulations, you got a botnet that's 100,000 strong. And it just did that with a lot of them. And as a result, we ended up in a situation where this guy got a very big and powerful botnet and was able to do a terabit of traffic for flooding. So that kind of highlighted some of the significance of some of this stuff. Another thing, like I said, there's static certificates and keys are worth checking. And if there's any services like a web server, Apache, Light HTTPD, etc., check to see if there's service files there that you can look into that might be worth exploring. So I also said exploring the boot up process. So like I said, these things need to start off, fire up everything they need automatically, and just be good to go for the end user. So usually you're going to want to look at the init system that's on there, whatever that may be, and look at how that's configured to start up. So there's usually going to be initialization, stuff like that, and it's usually going to create a RAM disk for temporary storage, for file uploads and stuff, or moving the configuration from the flash so it doesn't have to keep trying to read from flash. There's configuration of settings, so a lot of times it has to read what the user saved into the config, which is stored in flash, and then actually make those configurations. And then also sometimes there's first boot initialization. It's worth seeing if there's any of that sort of stuff there. Sometimes you can find that they do some sort of private key creation or etc. And it's worth exploring that stuff. If it's doing anything that's going to make use of a pseudo random number generator, has it set the time first before it started trying to use the pseudo random number generator? If it hasn't, then there's a good chance of predictability in some of those keys that get generated. But part of this enumeration of the boot up process is to figure out what's getting launched and how it's configured. Once you know that, you know a lot of your attack surface and what these services are. And honestly, too, comments, some of these init scripts and stuff like that get started, sometimes you can find comments in them that are comic gold, where you can tell the developers were just having a bad day. So, yeah. So next up is we move on to looking for exploits. After we figured out, these are the things that should be running, let's try looking at things. Is Telenet or SSH running? If it is, did you crack the password successfully? You can just log in at that point. And like I said, there was a mirror botnet that actually made use of that. There was another botnet that went around as well, which was called BrickerBot, which is what that code is on the bottom right there. It would actually attempt to just use dev-urandom to literally trash any storage on the device and then reboot. So it was designed to basically brick the device if it infected it. And that was apparently somebody's attempt to deal with the botnet that was spreading the mirror botnet and basically just say, these things are insecure, let's just destroy them. So, yeah, it's definitely worth an attack. Another thing to consider as well is I've seen some devices that will actually start Telenet or SSH and then take the IP tables and block the port to SSH or Telenet, but they only did it for IPv4 and forgot about IPv6. And so if you issued it an IPv6 address, you could actually then just Telenet and SSH into it because the firewall rule didn't cover IPv6. So worth considering. Continuing again with some of the low-hanging fruit, you've got web interface. Is it an actual real server like Apache or Light HTTPD, which are very common, or did they do the absolute horrible thing of trying to think that they're smart enough to build their own web server from scratch. I've seen that happen a lot, and it usually does not end well. But it is actually more common than you think because of custom authentication mechanisms or watchdogs that they would actually want. Most watchdogs, if you're not familiar with a watchdog, a lot of these like SOC system on a chip support a watchdog mechanism, which is your program will open it. It'll usually be under like dev/watchdog. And once you open that, if you send it a heartbeat, you have to keep sending it a heartbeat. Or if it goes with a timeout where it doesn't get that heartbeat in a certain time, it'll actually just hard reboot the system. This is designed for stability. So what you do is you take your critical process and make it activate the watchdog. And if that process died for some reason, the device would auto heal basically by doing a reboot. So as a result, though, there is a catch to this. Only one process can have access to the watchdog. Once it's opened by that process, that's the only process that can talk to it. So a lot of times they'll try to go all in where everything is on one device or in one process. And if that one process crashes, it reboots the entire device. So, but either way, custom HTTP servers definitely deserve to go under the microscope. HTTPS, like we said, if there were static HTTPS certs, it's definitely time to explore those. There was actually a pretty cool little project that was going on for a while, which was called Little Black Box. It's not been updated in a very long time, but this was actually a SQLite database that had public-private key pairs for a lot of different embedded devices. Dev TTYS0 was the guy. He actually used to do a lot of embedded device hacking. So he made it a point to capture and log those into a database anytime he saw those and captured the fingerprints for those. So if you were scanning a device and you got a fingerprint for an HTTPS server, I could actually just query my database to see if I know that fingerprint. And then I had the public-private key pair, which would allow me to decrypt any HTTPS or traffic to and from that device, which is not great, given that most devices are configured through a web interface. So authentication is another thing to consider. Is the authentication appear, like say that it was using light HTTP, is this going through a directory-based authentication, or is this a per file, or is this even a custom authorization or authentication system? Did they forget to secure something important if it's in the more granular category? Being that you have the firmware file, and you've extracted the file system, it's worth going through the web root and just creating a catalog of all of those items. And this actually makes it so you can do a really quick Durbuster attack that will have high success because you already know what the files are. And then how is server-side logic handled? So is this using CGI files? Is it how is code execution done server-side if it needs to be done? Going on from there, how are settings stored on the device if you got access to the device somehow? Are settings being stored clear text? Is it easy to actually get to these? Are there any sort of UARTs and stuff like that that you could actually access that would let you make it pretty trivial to dump the stuff? Does this device allow for configuration backups, and are they encrypted? If not, then that's kind of a finding in and of itself. If it is encrypted, ask yourself, is it really encrypted, or are they just doing something like XORing it? XOR is usually pretty easy to pick up on because, like, a lot of times I've seen these config files, they're just dumps of the configuration block of the NAND. And if you start seeing a repeating pattern in very large chunks, that's often where it either had FF or hexadecimal value FF or a hexadecimal value 00. And the key was there. So it's either the key itself or it's the key by FF or whatever. And that usually makes decrypting these things very trivial once you see that. Are there any ELF files that are running any homebrewed services? There's a lot of devices out there where they create their own protocols. The problem is a lot of people are really bad at creating protocols from the ground up. That's why we try to leverage like a lot of known protocols. Yeah, this not a great ideal either. So if you encounter that, it's definitely worth putting that underneath the microscope if you have the time to do so as well. So deeper analysis, web roots. like I said, if we had found that it was using a scripting language or CGI bins binaries, it's worth looking into those. The script files are usually pretty straightforward and are going to be just scripts, so you can just human readable, just peruse through the code and find what you want. If it's not that and it's a binary, then I usually would try to target and look at these things and use strings to kind of look at what libc libraries or C++ libraries are being invoked and functions that it's going to try to import. And think like system, string copy, sprint, these commonly vulnerable functions would help you figure out which ones you actually want to look at and really put under a microscope, because it's like if you're using string copy or system in a CGI binary that's in a web root, I would consider that probably more prone to be exploitable in some way, and it's worth looking at. Another thing in the web root to consider is symlinks. If symlinks are there, where do they go? I've seen some instances where these symlinks actually went to an SD card or a USB device that could be plugged in. And if that's the case, then you can actually just put a CGI file on that, plug it in, and access it in the browser, and you've got a shell. That's a very easy way to exploit some of those systems if you have them. It's also where it could go. Like it could actually lead to the temp folder, and that could also be where if you uploaded a file for an update, that could be where that goes, and you could actually possibly end up in a situation where you have a trigger for RCE. So another thing is when it comes to file uploads, again, how well do they handle sanity checks? Like there's probably a certain format to the file that's being uploaded. Are they actually validating that or no? So that's definitely worth inspecting. So we had kind of pointed out that there were CGI files that were there, and you might want to look over those. There's a few tools for that. You've got Ghidra, which is the NSA toolkit that came out. That's pretty good. And IDA Pro, which is a commercial option, but it's actually pretty good as well. I think both of these are great tools to use. And I found that they work best. Like if you're doing this stuff professionally and you have access to IDA Pro, awesome. Just make sure that you get the licenses for the Hexray kit so that you've actually got the full decompilers. Really good tool. I find that these two tools actually complement each other very well, not one or the other. Just keep both in your tool kit. In my opinion, most of the time, it's best to have more than one tool in your kit. These two are very close to each other, but they complement each other, in my opinion. So you can use those for that. And like I said, those tools were kind of used for being able to reverse engineer, decompile, and disassemble. That's static analysis, and that's all good and well. But sometimes you need to run code dynamically. And like say that you're trying to debug an exploit. You may want to be able to run through debugging your exploit by actively running it. And that can be kind of hard because it's like, okay, so if it was an ARM-based thing, maybe I can throw it on a Raspberry Pi. Maybe that would work. Sometimes it won't because of the way that they laid out the file system. It's not going to really line up with Raspbian. There are other ways to do this. There is a tool called QEMU. QEMU will actually let you emulate another architecture on your system, and you can use that with BINFMT, which can actually detect what a binary is, the format of it, and then try to invoke another loader for it. And between those two tools, you can actually now run ARM natively on your x86 machine. Combine that with GDB, and you've actually got the ability to debug an ARM binary on your x86 architecture as well. So these things combined, and GEF is another tool. It's a plugin for GDB that makes debugging a lot nicer. Combine these things together, you've actually got a winning platform for debugging and creating exploits for another architecture. So you can always try to find, like I said, evaluation boards, but some of them get kind of hard. So like, for example, PowerPC, it's hard to find a cheap evaluation board for PowerPC. Like you can hack an old Nintendo Wii or something like that and maybe get a PowerPC that way, or a really old MacBook, but it's not the best ideal. Same thing was like, there's an architecture called Super H4. It's hard to find embedded development evaluation boards for that. So this can help because QEMU can actually emulate those things for you, and it's incredibly useful. Another thing that's really useful about QEMU is there's the -G switch, which will take a port number as an argument with it. And what that'll do is when it starts up the application, instead of just launching the application, it will actually inject a GDB server stub and listen on a port and wait for GDB to connect first. And then it'll actually start the application debugging into GDB server. So all you need to do to install that one is just QEMU user static, and you should be good to go with that. BINFMT, like I said, is a loader that kind of detects what the file format is and then tries to inject or pull in the appropriate loader. So in this case, it would actually say, hey, this is an ARM binary. Let me actually invoke QEMU and go from there. One thing that's really cool about this too is that it can actually support, like under Etsy, you can create a QEMU-BINFMT folder. And then under that, if you put the folder for like /ARM, you can actually make that a symlink that would point to the firmware. If you try to load a binary, it will actually look to that folder for where the libraries should be that that binary wants to load, and you end up getting things in there. So you should be good to go. There's actually the Pwned tools documentation actually has a really good write-up on how to set all that up. So, and then we've got GDB. You should already be familiar with this one, but it is worth noting that if you're on Kali, you want to install GDB-multi-arch so that way it's aware of ARM, MIPS, and all these other architectures, not just x86 or whatever your native machine build is. And then GEF is, like I said, it's a Python extension. GDB now supports Python. You can actually use this to sideload some things that will actually, like GEF, which is GDB enhanced features, will give you a massive, massive, massive quality of life improvement when you're debugging things. So, and this one is actually supports multiple architectures, and it's got a lot of functionality that's just helpful for reverse engineers. So kind of as a demo, I kind of wanted to explain like my firmware that I just demonstrated extracting. I put a binary on there that was under user/bin/exploit me, which had a very basic buffer overflow exploit in it. And the goal of that is we're going to try to exploit that on our x86 system to invoke a function called never called, which is never called. And basically, the agenda here is we're going to kind of run through the slides a little fast here because I realized the time. But let's review the source code for clarity. Now, normally in a normal circumstances, you wouldn't have this, but we will have that just so you can see what that is. Setting up the QEMU BINFMT so that way we can actually run and test the binary, and then show how to use Ghidra for reversing it. Find the bug and the address for where our never called function is. Save the figure out how to figure out the offset for that stuff, and then finally building a POC exploit for this. So we'll go through this real quick. So I wanted to first go over the source code here. So this is the actual code for the binary that I created. And the main function here, which is the entry point for a C program, would actually just check to see, did we get an argument? If we didn't, then we're going to print the usage, which would be the program name plus your name. It's asking you to provide one. And then we will basically use string copy to copy this to a buffer that's only 128 bytes long. That's our buffer overflow right there due to the use of that string copy. We will do a print hello to the user, whatever they provided as their name, and then we will return 0. We have this function up here called never called, which is never called. It is basically just going to print a little message out that just says you win, and then exit with a status code of 1. And that's it. So our goal, like I said, was to exploit the buffer overflow here and then try to invoke and call that never called function. So for that, we would actually want to first set up that bin format QEMU. And we had extracted that firmware, and the root of the firmware file system would actually be under our home/Kali/ the firmware extraction path /squash fs -root. That would be like that file that when we ls it, you see the etc/bin or bin lib and so forth. That is where you have to actually set up this etc/QEMU-binformat/ARM to point to as a symlink. This folder here likely does not exist by default. So the QEMU bin format folder likely does not exist under etc. So you'll want to create that. And then you'll want to use the ln command with a -s switch. The -s as in Sierra switch is what actually tells it to create this as a symlink. And then we will point it to that fs root, which is where I did in this first command was the export that points to that long path. And then we will just use this for as a variable effectively, and then tell it that that's where we want it to go. So if we had this, that's done, we can actually do this ls-l, and you can actually see we've got this ARM folder here, and that is a symlink to the root of the file system. Once you've got that in place, you should now be able to actually just run the binary as though it were a native binary. So in this example here, I've got this screenshot here. We can do the file on this user/bin/exploit me. We can see that this is an ARM binary. And then if I want it to, I can actually just invoke it like it was a normal program. And you can see it's actually running, which this is an ARM binary on my x86 or x64 system. Runs just fine. And then we can, by just running it natively, we get that usage message that's asking us, explaining how to use the program, effectively telling us that we need to provide another argument that's our name. And if we provided it was testing, it would say hello testing and so forth. If we want it to as well and not use the bin format, you can directly invoke QEMU-ARM-static and then invoke the binary that way. But you don't really need to, because we set up the bin format. You can actually just run it like it's a native binary, and it works pretty well. Ghidra was another tool that you might use if you wanted to try to figure out where some of these offsets are. So we can actually just create a new project in Ghidra. If you've ever used it, import the binary for the exploit me, and then we can use the code browser to kind of look at it and look at the decompiled output, and then find the start and end offsets for main. And the reason for that is when you get into GDB, it'll make it easier to create breakpoints on the start and end of the function that you think is vulnerable, assuming it's not a pi binary where it's position independent. In this case, it's not. And then we would actually have to find the offset for never called as well, because when we exploit this buffer overflow, we want that to be where we return to whenever we hijack the PC, which in ARM is, if you're familiar with x86, you had EIP, which was the pointer that would tell it the instruction that's going to execute. In ARM, it's the PC pointer, the program counter. It tells it where the offset for the next instruction that needs to be executed. So if we looked at Ghidra, I'll actually just leave it to the slides for time constraints, but you could actually use the decompile that's in there and basically clean up your code a little bit, and you would end up with something like this. This is the decompile frame. There's the disassembler view, which would allow us to actually see, we got our main function. We can actually see the start of main is at 0x10454. And the end of it would be 0x104D0. And this is the important one because this is the instruction that this is basically the equivalent of a return. So this is a load multiple immediate address, and it's going to tell it to look at the stack and pop two values off of the stack, and one goes into R11, and then the other one goes into the PC register. So that's basically the equivalent of the return instruction that you're familiar with from x86. So we also needed to find that never called offset. And one of the easiest ways to do that would probably be to look for that puts instruction or this date underscore and then some address. That is pointing to a string that is our address to the string you win that we would print. So we could actually find that and then use a cross-reference to figure out where it occurs in the code, or just kind of scroll through it. Since this was such a small binary, there's not a lot of code here. So once we found that, we can actually find that this part here in the black, the 0010438, is our starting offset for this function. So once we've got that, we would need to find the offset for how many bytes of junk do you need to provide to reach where PC is and overflow that value, because that's what allows us to take control of the execution flow of the program and redirect it somewhere else. And the easiest way to do that is while we've got our program running in QEMU, we can use that -G switch to allow us to use GDB to connect to it, and then we can run it and just basically debug it and then crash it. And the best tools for figuring out the offset here is still going to come from Metasploit. It's the pattern create and pattern offset tools. So running Metasploit MSF pattern create -L, we're telling it to create a string that's 200 characters long. And this is a cyclical pattern. So what will happen is when the program crashes, we can start this up in GDB, we can set our breakpoints, and then we can continue. And then what will end up happening is when this program crashes, we'll actually see, once it reaches that last instruction where it's going to do the load multiple for popping R11, popping PC, we can actually see this value here. And if we take that value that's there, because that's actually basically an ASCII string, if we take that value and return that to pattern offset, until we generated a string that was 200 characters long, and this was the value that was going to override PC, it'll tell us exact match at offset 132. That means that we would need 132 characters of junk to reach that offset that is actually going to override the PC value. So we know that 132 characters and then the next 4 bytes that are there are going to be what actually overrides the PC value. So once we've got that done, we can actually start working on our buffer overflow POC. So we know the number of bytes because of the pattern create and offset tool. It's 132 bytes. So we can create a variable called junk size, which will just kind of store how much junk we need to create. There's the address of never called. We'll go ahead and just put that into a variable so that way it's easier for us to work with. And then I like to use Pwned tools for writing some exploits. So there's a nice convenience function here called randoms with an S there. If you provide that a number, it'll generate a random string of junk that's the size that you specified. So this would give us an exploit that would be 132 characters of junk characters, so just random trash string. And then there's a function here, we're going to do a plus equals, which will append this value to it. And then we've got this P32, which is pack 32. So it's going to try to pack this as a little Indian value. So basically reverse byte order. And it's going to be the address to never called. And then we're going to do decode so that way it would kind of convert it into a string. And then we're going to do a print. And then we're going to do -1 here because we've got, 38, that's a byte. The second byte would be 04, and then the next byte would be 01. And before that, this is a 32-bit value, there would have to be a null byte there, and we don't want that included. So we will do the -1 to get rid of that last byte, which is the null byte, because we don't want that because this is a string function and a null byte's a terminator. So once we've got that in place, we can actually just run that. So if we just run the Python 3 was the exploit, you can see you get a long string of gibberish there. We can actually run that that exploit me binary, and then we can just use the $ begin parentheses and then our command and there. And what that'll do is that'll run that command, and the output that comes from it will get dropped straight into the shell and passed to this program. So as an argument. So you can see it said hello there, and it had that long string of gibberish. And then at the end of the program's execution, you get that you win, which came from never called, which means that we successfully hijacked the execution flow of this program and ran that. So no, I ran a little long here, but do we have any questions?